Okay, my name is Jim Garrison. I'm in engineering. My expertise is in satellite remote sensing. And I want to talk about the essentials, food and water. And water is essential for growing food. Agriculture is a majority user of the water supply. And water is becoming scarcer and scarcer. So managing of water is very important. And in order to properly manage water, you need to be able to sense the water that's being used for things like precise irrigation, variable rate irrigation. And what's the key measurement to measure in sensing water is what's within the soil down to the layer that the plant roots absorb it, or the so-called root zone soil moisture. So there's two ways of measuring soil moisture. One is to actually install some sensors in the ground at multiple depths. Each one of these will make one measurement. They're approximately $100, $200 each. They have to be maintained. The data has to be collected. Whoever installs them there is responsible for them. So the more sites you want to measure, the more precise tracking of your water usage, the more sensors you need. The other way is in remote sensing. If you're using satellite coverage, which could generate maps of global soil moisture every 1 to 3 days, which is really good for studying climate and the environment and doing long-term predictions. But as far as precise control of irrigation, we deal with a 10-kilometer resolution, which isn't really that useful. Also, the frequencies that are used for satellite remote sensing can only penetrate the soil to about 5 centimeters. So they rely on physical models to predict the subsurface soil moisture. So I'm proposing a new technique that I've been developing for the last few years that uses satellite data in a slightly different way. It uses the reflections of communication satellite signals as a source for measuring the subsurface soil moisture, or what we now call signals of opportunity, or SOOP, or SOOP. And we look at any communication satellite. We don't need to have any authorization to use it. We just look at it as a signal source, and then we compare that with the reflected signal. And the reflectivity of the surface is a function of the soil moisture. And we're looking at a specific band of satellite communications, what's called P-band, maybe also called UHF to the communications people, but the scientists is called P-band. And P-band penetrates typical soil down to about 15 to 20 centimeters. And through using these existing signals, we get around most of the requirements for being able to license a transmitter in P-band, which is extremely difficult, and the size of the antennas required. So as far as a research activity, we've done some experiments using a larger instrument I'm going to show on the next slide. And these are typical measurements that we get. These are some ground tracks from an aircraft. You can see some variations across the soil moisture. As a test, we fly over a lake, and we have a very high reflectivity over the water. So this is the instrument that we've used to collect those measurements. It's a prototype. It was developed under what's called an instrument incubator grant from NASA for about a $4 million project. Obviously, that fits onto a piloted aircraft. It would not be that economical to use. This is the antenna, and that's one of the main limitations why we need a piloted aircraft. We've done some work and some fancy signal processing. We think we can get away with using just a little simple dipole antenna like this and shrink the electronics down to fit it onto a drone. So we're currently working as a student project as a follow-on to this grant, something called P-SOOP, P-band Signals of Opportunity, with the goal of taking this and putting onto a drone for effective monitoring of root zone soil moisture for precise agriculture.